I'm going to go through a few trig identities, or really how we can go from some complex phases to different trig identities. And this comes up a lot when we're starting to do time dependence in the energy basis. So some people might just memorize these and say, oh, you have to memorize the trig identities. We can really just figure them all out if we know this basic idea. So this step you kind of need to be able to just know. But again, if you draw the complex plane with the real horizontally, the angle up from real, and then imaginary on the vertical axis, you would get this. So now let's say we have a negative angle. We can just plug in negative theta, but then if we think about the relationship or the symmetry of cosine and sine, we actually see that cosine of negative theta is the same as cosine of theta. And that sine of negative theta is the same as negative sine of theta. So one thing we could do right now is we could actually add these together. So let's take e to the I theta plus e to the negative I theta. Well, we see here that I'm going to have cosine theta plus cosine theta, which is 2 cosine theta. And then I have I sine theta minus I sine theta, which is 0. There we go. The way you're going to often see this written is that cosine theta is going to be e to the I theta plus e to the minus I theta over 2. So that's a relation that you might have seen written somewhere in the back of a book, but you can get it just from knowing this. So if we subtract them, we'll get the other one. So e to the I theta minus e to the negative I theta. Cosine minus cosine is 0. And the reason why I'm kind of breaking it up that way is that this cosine term is real. This sine term is imaginary. So you can kind of think about grouping your real terms together and grouping your imaginary terms together. So cosine minus cosine is 0. But then I have I sine theta minus I sine theta. So that's 2I sine theta. And so in that case, I could say sine theta is equal to e to the I theta minus e to the negative I theta over 2I. If you wanted to, we could rearrange this. We could, for instance, multiply both the top and the bottom by I, if you don't like I on the bottom. So that would give you an overall I. But because we've multiplied I on the bottom, that would actually give us negative 2. So it's not really very nice to write it this way, right? So what you could do instead is say, oh, we'll just flip that around. And so if you want to keep that I separate and on top, you would actually flip the signs here. And this would become e to the negative I theta minus e to the I theta. But normally we write it this way. So this relationship we can derive from these, and that's pretty important. So what if then we have a term that looks like e to the I a plus b plus e to the I a minus b? Sorry, I mean for that to be multiplied. Let's multiply this. No, I did mean plus. This is what happens when I don't look at my notes. So now, one of the things we can do here is actually factor these out. So we have e to the I a, e to the I b, plus e to the I a, e to the I negative b, right? So if you wanted to do it that way, you would have e to the I a, and then we would have that positive plus that negative 2 cosine theta, where theta is now b. So if you start to see something like this, this would be a different way to write it. So recognize that we're going to get some complicated things in our exponents, and you're going to need to start shoving it around in different ways to be able to get it into other forms like this. So I'll stop there. Again, the key is to just get comfortable using this and realize that when you're doing quantum mechanics, especially when there's an interference term, you're going to start to see some complicated things happening in the exponent, and you're going to need to be able to recognize when you can, like, oh, let's break it apart, simplify it this way. Is this better? Does this help? Sometimes it will.